Okay, we move on. So I just talked about the Kronecker delta. Another guy to keep in mind, doesn't show up that often. I think it's number 3, but it's still quite useful. Is what's called the permutation tensor, but for the purposes of this class, just call it permutation symbol. Okay? And it's denoted by capital epsilon. It has 3 indices, I, J, and K, and it has the following property. It is 1 when I, J, K are clockwise. Okay? So, for example, 1, 2, 3, or 2, 3, 1, etc. Okay? It is -1 when I, J, and K are counterclockwise. So, for example, if it is 3, 2, 1, okay? In other words, I is 3, J is 2, K is 1, etc. Then it's -1. And it's 0 for the rest. Okay? So the way to keep this in mind actually is nothing more than if you see I, J, K, I follows J, J follows K. In other words, 1, 2, 3, then it's +1. If it's in the opposite sense, it's -1. And then if there is no sense, which means some of them are repeated, obviously, because there are only 3 IJKs here, then it's 0 everywhere else. Okay? And so because IJK and are +1 and -1 in the sense of order, an important thing to keep in mind is epsilon ijk is equal to minus of epsilon kji. I apologize. Ijk, that's the same. I kj. 1, 2, 3, 1, 3, 2. Okay? 1, 2, 3, 1, 3, 2. Okay? So if the last 2 indices are flipped, then it's the negative. The only time, well, one of the times when epsilon comes into use is when you look at cross product of 2 vectors. Okay? I know different people are taught in different ways of how to compute A cross B, but the index notation saves us all. This is simply epsilon ijk aj bk. Now, here is something to pay attention to. We have 2 repeated indices, which are j and k. So this is sum over j going from 1 to 3, sum over k going from 1 to 3 of epsilon I, j, k, a, j, b, k. But there's still an I floating around. We don't know what value I takes, but that's fine. Why? Because A cross B gives you a vector that's perpendicular to A cross B, right? A dot B gives you a scalar. A cross B gives you a vector, which means it has 3 components. each of those components are represented by I. So if you want to be very precise, the way you would write it is A cross B, the ith component of A cross B is equal to epsilon ijk aj bk. Okay? I leave it as an exercise for you to actually expand this out and write epsilon I11, A1, B1, etc., etc., etc. Okay? And the other little formula that is worth, it comes into play a lot, is the relationship between the permutation tensor and the Kronecker delta. So epsilon ijk times epsilon ilm, so it has one common index here, I. This can be written as a product of deltas. This is delta jm, j from here, I can write jl, yes, and kn minus swap them. So delta jm, delta kn. Okay? That's pretty much it with the permutation tensor. Okay. Fourth thing is some rules about indices. Okay? So rule number one, free indices should match on both sides of an equation. Okay? By that I mean, if you have an expression that says AI is equal to BI, that is fine. Free index is I on the left, free index is I on the right. This is saying vector A is equal to vector B. Okay? An expression with more than one indices, Aij, Bk is equal to Bk, let's say J. Okay? Is equal to Mij, and Kj. Okay? Here I and K are the free indices, so they should match. This is not equal to Mij and Nlj. Okay? This L is floating on the right hand side. This K is floating on the left hand side. Here the I matches I, K matches K. I matches I, but K doesn't match I, so you're in trouble. So this is not allowed. Basically, whatever index you have on the left, free indices, you can have more than one on the left, should match the ones on the right. The second is repeated indices are dummy or replaceable. Okay? Which means if you have an expression AI BI, now it is okay to say it's AK BK. Why? Because they represent sum. Okay? So they're going to be summed up. So this is just a placeholder to say I will always go from 1 to 3. This is a placeholder here to say K will always go from 1 to 3. So in this case, this expression is valid. So when you have a repeated index, you can replace it with whatever you want, okay? As long as you replace both of them. Yes, okay. Very good. So let's simply put what we know into action now. Okay? So basics of vector, addition, so let's say A plus B is equal to C. In index notation, this is simply saying AI plus BI is equal to CI. Okay? Note, even if you have two i's here, that doesn't imply summation because they are separated by an operation here. So if you had AI, BI, then that implies summation. But AI plus BI does not imply summation. Okay? Just a subtle thing to keep in mind. Let's move on. A dot B, we saw it already. This is equal to AI BI. A cross B, ith component of A cross B is epsilon ijk aj bk. Now, it's probably time to introduce another notation, which is dyadic notation. So you're neither doing a dot product or a cross product, but you are doing a dyadic product, which is a cross inside a circle. This is a bizarre quantity, bizarre looking quantity now, and following the logic ij. Okay? So dyadic operations are operations that take you from a tensor, vector space to tensor space. For now, just remember that if you see this notation with a cross inside a circle, that implies you get a two-dimensional object. Okay? We will see more of this when we actually do continuum mechanics. Okay, let's do calculus. So, remember our coordinate systems were x1, x2, x3. Okay? So, derivative of xi with respect to xj. Okay? What will this give us? So, if I was equal to j, we would have derivative of xi with respect to xi, which is, for example, what is the derivative of x with respect to x? 1. Or derivative of x1 with respect to x1? 1. Derivative of x3 with respect to x3 is, again, 1. But what is the derivative of x1 with respect to x2? Or if you prefer derivative of x with respect to y, that's obviously 0. And what does that remind you of? If I equals j, then the derivative is equal to 1. If I is not equal to j, then the derivative is 0, which is our Kronecker delta. Okay? So that's the one simple partial derivative. Again, in our class, in the continuum mechanics class, we will encounter derivative of two-dimensional objects with respect to itself, aij, bkl. Okay? And this is equal to delta ik, delta jl. Okay? Which is a statement that when I equals k and when j equals l, only then it's equal to 1. Okay? So A12, 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 A13, it's 0, etc. And this can be chained for any higher dimensional objects. Okay. So those are some basic rules. So let's put them into action. Okay? I will leave this expression here because we will use it. And it's probably worthwhile while I erase this guy to actually take a nice long break, have a cup of coffee, come back because this is going to get more and more tedious. So, I have nothing to say other than clean this up. Okay, almost there. Okay, let's put these guys into action. Okay, let's do, excuse me, something that probably haunted you when you were in high school. These kinds of crazy vector operations. Okay? If you don't remember, it's fine. It definitely bloody haunted me. I would always memorize it. But now, thanks to index notation, we can go after it. Pretty straightforward. Okay? A cross B, the ith component is epsilon ijk aj bk. Okay? C cross D, ith component is epsilon I. Remember that you can only have two repeated indices, so I can't use J and K anymore, so I'll use M, N, Cn, and Dn. Okay? Let's take pull a step back. Let me call A cross B, since it gives us a vector, let me call it M dot N. So this is N, right? A cross B is N, C cross D is N, and I'm looking at the dot product. Dot product of M and N are Ni, Ni. So I need to take the ith component of A cross B, I need to put it next to the ith component of C cross D, which is what I did here. The ith component is epsilon I dada, and ith component is epsilon I dada. Okay, let's put it all together. This is equal to, so I bring I, J, K, epsilon. Now it's all just products. So I, M, N, A, J, B, K, C, M, D, N. Now we make use of this property that there is a common index which is I. So this is delta Jn delta Kn minus delta Jn delta Kn, and this long train of Latin alphabets. Okay. We now appeal to the generosity, if you like, of deltas. Okay? Delta Jn Aj. Remember, delta, whenever it sees a common index with its neighbor, it happily sacrifices itself and gives its free index to the neighbor. So Jn, Aj, so this becomes An. And we continue like this. Kn, Dn. So I can delta Kn, or if you want, we can take Bk. Delta Kn and Bk. Okay, K is common, so B gets the free index N. Minus, sorry, I forgot the other guys. Cn, Dn. Minus delta Jn, Aj, N is free, so this becomes An. Delta Kn, Bk, Bn. K is common, N is free, so it becomes Bn, Cn, Dn. Okay? Now what do you see here? Am, Cm, Bn, Dn. Bn, Cn, An, Dn. That should remind you of dot products, right? So this is A dot C multiplied by B dot D. In index notation, you stop here. This is your answer. But we will bring it back to the vector notation so that those of you who remember your tortured childhood with vectors may recognize this. Minus A dot D multiplied by B dot C. Okay? So, if you eventually, and I'm sure you will, become proficient with index notation, then you get to your answer in 1, 2, and 3 steps. Okay? And if you remember how painful it was to do it in the classic vector way, you'll realize that in 3 lines you actually arrive at this solution, which is pretty cool. Okay, so we carry on, and I think I'm breaking some of the rules here, but so be it. Okay, let's look at this funny looking object. R is equal to square root of x, k, k, xk, xk. Okay, what is this? This is just the norm, if you think about it. And in index notation, it is not nice to write square root of xk squared, okay? Because you don't know what you're doing with k. If you have 2 k's, you know it's x1 times x1 plus x2 times x2 plus x3 times x3. So this is just square root of x1 squared plus x2 squared plus x3 squared. Yeah? So it's just the norm or the distance or whatever you want to call it. Okay, so the question here is, what is the derivative of r with respect to xi? Okay, all right, derivative of square root of something blah 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 is 1 over 2 square root of that blah blah. Okay, and now what is remaining is xi of xk, xk. Okay? This is where the subtlety of index notation comes into play. So this is 1 over 2 r, because it's the same, times derivative xk times derivative of xk with respect to xi, which is delta ki, plus xk, derivative of xk with respect to xi, which is delta ki. Xk delta ki is nothing but xi, and same here. So that's 2xi, so this is xi by r. Okay? So on and so forth. We'll see more applications of this pretty soon. Okay.